In this video, I'll be going over other indeterminate forms of limits. So in the previous video, we looked at the indeterminate forms that were 0 over 0 or plus or minus infinity over infinity. And we saw that if we were evaluating a limit and we ended up with 0 over 0 or positive or negative infinity over infinity, we would use L'Hopital's rule. So L'Hopital's rule works well for those types of limits. But what about limits that are in other indeterminate forms? So what about limits that equal something like this? Either 0 times plus or minus infinity, infinity minus infinity, 1 to the infinity power, infinity to the 0 power, or 0 to the 0 power. There are many more other indeterminate forms, but what about if we have a limit that by direct substitution we end up with something like this? And before we get into how we approach these types of limits, I kind of just want to say why these are indeterminate forms. So, for example, 0 over 0. When we're first learning about division, we know that, well, anytime we have 0 divided by anything, let me just say, so if we have 0 divided by some number a, that is always equal to 0. However, we also learn that we don't ever want to divide by 0 because we say that that's undefined. So what we have here, we have competing interests. We have 0 divided by something, so in one sense we want to say that that is equal to 0. However, we're dividing by 0, so in the other sense we want to say that this fraction is undefined. And so in each of these indeterminate forms, we can think about what this could equal in two or more ways, and we could think about this as kind of a tug and war between the basic rules that we know about computation. So how do we approach these new indeterminate forms? And we can still apply L'Hopital's rule, but we might need to do a little bit of work to get to that point. Alright, so our first limit we want to evaluate is the limit as x goes to 0 from the right hand side of x times ln of x. Now, first thing we probably always want to try when we're evaluating limits is use direct substitution. And what we're going to get here is 0 times negative infinity. Remember, the graph of ln of x looks like this. So as the function gets close to 0, ln of x is going to negative infinity. So this is an indeterminate form, right? So 0 times negative infinity. In one sense, 0 times anything we want to say it's 0, but infinity times anything we would want to say that that's infinity, or negative infinity in this case. So we kind of have these two competing interests. Because this is an indeterminate form, we want to get to the point where we can use L'Hopital's rule. So that's an indeterminate form. The problem is, to use L'Hopital's rule, we must have a quotient. And right now, this is not a quotient. So what do we do? Well, we can rewrite this limit as a quotient, and we can take this x, and if we divide by 1 over x, that is the exact same thing. So ln of x divided by 1 over x is the same as x times ln of x. So now we're allowed to apply L'Hopital's rule. So we're going to say apply L'Hopital's rule to this guy right here. So recall, all we need to do is, before we will apply L'Hopital's rule, but I'm getting a little bit ahead of myself. If we were to use direct substitution here, we're still going to end up with an indeterminate form. This time, though, it's going to be negative infinity divided by 1 over 0 from the right-hand side. That's also approaching positive infinity this time. So this is still an indeterminate form. So sorry, I was getting a little ahead of myself. We want to make sure that we have an indeterminate form before we apply L'Hopital's rule. Initially, up here, we knew that that was an indeterminate form. But the question was, well, when we rewrite this as a quotient, is that still an indeterminate form? And it is. So we're going to apply L'Hopital's rule to this new limit. So we're going to say the limit as x goes to 0 from the right-hand side. The derivative of the numerator, the derivative of ln of x is 1 over x. The derivative of the denominator, well, 1 over x, it might be nice to think of this as x to the negative 1. And we apply the power rule. We're going to have negative 1 times x to the negative 2 power. So this is negative 1 over x squared. So negative 1 over x squared here. Simplifying this complex fraction, the limit as x goes to 0 from the right, this will be equal to negative x squared over x here. So before we even do any substitution, this is going to be equal to the limit of x as x goes to 0 from the right-hand side. I can divide or factor out an x in the numerator and the denominator here, so we end up with just negative x. And so by direct substitution, this is going to be equal to 0 here. Okay, so the limit that we were originally presented with is equal to 0. Okay, our next example asks us to evaluate this limit as x goes to 0 from the right of 1 over x squared minus 1 over tangent of x. Let's try direct substitution and see where that gets us. 1 over 0 from the right-hand side, so we're getting really close to 0 from the right. So we have 1 divided by really small numbers, and those are getting squared. But that first term is approaching infinity, minus 1 divided by tangent of x. So we can remember what the graph of tangent looks like. Something like that. So as x is getting close to 0 from the right-hand side, that is going to be this part of the graph. I'm trying to trace this here. It's going to be this part of the graph, but as we're getting close to the origin, that graph is getting close to 0. So this fraction here, 1 over tangent of x, it's getting close to 1 over really small numbers, and again, that is going to be infinity here. Okay, so this is an indeterminate form. Infinity minus infinity. Again, we may think that that is 0. Anytime we have a value and we subtract that same value, we think of that as 0. However, there are different types of infinity. In other words, there are different, in a sense, magnitudes of infinity, and we don't necessarily know if these are the same, if these infinities that are written here are in the same magnitude or not. So this is why we actually can't conceptualize this as it's written. So this is an indeterminate form, so we want to see if we can use L'Hopital's rule. In order to do that, we need to rewrite the function we're taking the limit of as a quotient. So to do that, I want to get these two terms to a single term that's a fraction. So in order to combine these fractions, I need a common denominator, which is just going to be x squared times tangent of x. So in the first fraction here, I need to multiply the top and bottom by tangent of x. In the second fraction here, I need to multiply the top and bottom by x squared. And so we end up with this fraction. Now before we go ahead and use L'Hopital's rule, let's see what happens when we use direct substitution. Because if we don't end up with an indeterminate form, then we don't need to use L'Hopital's rule. So let's substitute 0 in here from the right-hand side. Tangent of 0 from the right, we already saw that that is going to be equal to 0, minus 0 squared is still 0, and then in the denominator I just end up with 0. So again, this is an indeterminate form. So because of that, let's apply L'Hopital's rule. So the limit as x goes to 0 from the right-hand side. So let's take the derivative of the numerator. The derivative of tangent of x is secant squared x minus 2x. The derivative of the denominator, well, we have a product in the denominator, so we need to use the product rule. So the derivative of x squared is 2x times tangent of x plus, keep the first function the same, times the derivative of tangent of x is secant squared of x. Okay, so now let's see what happens when we use direct substitution here. So when we substitute 0 into secant squared of x, it's the same thing as secant of x getting squared. Secant of x is the same thing as 1 over cosine of x. So when I substitute 0 into 1 over cosine of x, that's cosine of 0 is 1, so 1 over 1. So secant of 0 is going to be 1. 1 squared is still 1. So we get 1 in the first term, minus 2 times 0 is 0. In the denominator, well, I'm going to have a 0 here and a 0 here. So I'm going to have 1 divided by 0. So we're approaching 1 over 0, which we know is positive infinity. Okay, so to summarize what we have, we're going to say the limit of x, or as x goes to 0, from the right-hand side of our original function, 1 over x squared minus 1 over tangent of x, that limit is going to be positive infinity. Okay, so for this next example, we want to evaluate the limit as x goes to infinity of x raised to the 1 over x power. So again, by direct substitution here, we're going to end up with something like infinity raised to the 0 power. So this is an indeterminate form. So how do we evaluate this? Well, the first thing we want to do is let's let the limit that we're dealing with here be equal to L. Let's just set that equal to L for now. Okay, and then anytime we have an indeterminate form that has an exponent in it, we want to use some of the properties of logarithms. So let's take the ln of both sides. Okay, and by doing that, on the right-hand side, we can use the, first of all, we can say, well, the natural log of a limit is the same as the limit of the natural log of a function. So we can rewrite this as the limit as x goes to infinity of the natural log of x to the 1 over x power. And using the properties of logarithms, the power rule, this can come down in front. So we can rewrite this as the limit as x goes to infinity of 1 over x times ln of x. So hopefully this is looking somewhat familiar. We can rewrite this as a quotient, so ln of x divided by x. And by direct substitution, well, what we'd end up with is infinity over infinity, which is an indeterminate form. So that's a problem. We would now want to use L'Hopital's rule. So I'm going to kind of move everything over to the right here. So let's see. Translate everything over here. Okay, so applying L'Hopital's rule, I'll write it like this. The derivative, sorry, my phone is going off. Applying L'Hopital's rule, we want to take the derivative of the numerator and the denominator. So the derivative of ln of x, we're going to have 1 over x divided by 1. And by direct substitution here, we're going to end up with 0. So we get 0 over 1, which is just 0. Now, way back to the beginning of this problem, we said that we had this equation where the natural log of this limit was equal to 0. So I'm just going to rewrite that down here. And the whole reason we wanted to do this was because there's a property of logarithms a second property of logarithms that we're going to use. And that property is e to the ln of anything is equal to that anything. So e to the ln of a is equal to a. So what we can do here is we can say that e to the ln of L is equal to L. And we saw that ln of L was equal to 0. So I actually don't want to write this as L. I want to say, I guess I'll just go kind of in a roundabout way here. So we saw that ln of L is equal to 0. So so we saw that, but we also see that this property here, so e to the ln of a is equal to a. So kind of putting these two facts together, we could say that e to the ln of L is equal to L by this property up here. But we also know that ln of L was equal to 0. So e to the ln of L is the same as e to the 0. Okay, so ultimately what we're trying to find in this question is what is L going to be equal to? Because that's what we said was equal to the limit. So L is going to be equal to e to the 0 power, which is just 1. So our limit that we started with, the limit as x goes to infinity of x to the 1 over x is equal to 1. So if kind of what we did at these last couple steps isn't totally making sense to you, really pause the video and really sit with it and see if you can make sense. It may take a couple times. I know the first time I went through this, when I was learning this way back in college, this was a sticking point for me. Yeah, if this is a hang-up for you, really sit with this and see if you can work through this on your own. All right, and then in this last example, let's evaluate this limit as x goes to infinity of x minus the square root of x squared plus 1. Now we're going to do this one in a couple different ways. The first method will be eventually getting to the point where we can use L'Hopital's rule. So before we can get to that, let's just try to use direct substitution, and if we do that, we're going to end up with infinity minus infinity, which is an indeterminate form. The issue here is that this is not yet a quotient, so we need to do a little bit of work to get this to be a quotient. So when we're working with limits going to infinity, one strategy we can do with this term right here is to factor out the greatest factor of x. So I'm going to factor out square root of x squared. And what I'm left with is 1 plus 1 over x squared here. Okay, and I mean multiply that out, and you'll see that we get what we started with. And this factor right here, so the square root of x squared. When we take the square root of x squared, that's the absolute value of x. But because we're dealing with x going to positive infinity, this will always be a positive number. So we can just write this as x. So let's rewrite our limit. The limit as x goes to infinity of x minus x times the square root of 1 plus 1 over x squared. Now I have a common factor here. In each term it's x. So this is the limit as x goes to infinity of x times 1 minus the square root of 1 plus 1 over x squared. Okay, so now we have rewritten this limit, or the function as a product. So when we have a product, we can rewrite a product as a quotient. So let's go ahead and do that. So the limit as x goes to infinity. So this right here, this x, I'm going to rewrite that as 1 over x in the denominator. And then in the numerator, I still have 1 minus the square root of 1 plus 1 over x squared. Okay, so now that we have a quotient, let's see what happens when we do direct substitution. And in doing so, we're going to end up with 0 over 0, which is another indeterminate form. But now that, even though it's still an indeterminate form, it's different than what we had originally, because originally we didn't have a quotient where we could apply L'Hopital's rule, but now we do have a quotient. So let's apply L'Hopital's rule, which just means taking the derivative of the numerator and the denominator, and see what that gets us. Well, taking the derivative of the numerator is a little bit tedious. So the derivative of 1 is just 0, so I have negative, and then I'm going to rewrite this in parentheses. Like that. So using the power rule, I'm going to have negative 1/2, 1 plus 1 over x squared raised to the negative 1/2. And then times the derivative inside the parentheses, so using the chain rule, that's going to be times negative 2 over x cubed here. Okay, so that's what we'll get in the numerator, and I'm going to rewrite that a little, just to simplify things. So I have a negative 2 and a negative 2, those can cancel. So I'll have a positive 1 over x cubed times 1 plus 1 over x squared raised to the negative 1/2. Usually we don't write negative exponents, but we'll see that this won't make a difference in this instance. And then the derivative in the denominator, well, 1 over x, that's going to become negative 1 over x squared here. Okay, so we can do a little bit more simplifying. I have an x cubed and an x squared, so x squared is going to cancel. Into the numerator, I'm just left with 1 over x there. So I have 1 over x times 1 plus 1 over x squared raised to the negative 1/2, and that's all divided by negative 1. Now what we'll see is that when we do direct substitution, what do we end up with? Well, I get 1 over x, so 1 over infinity, so that's going to 0, times, I'm going to have 1 plus 0 raised to the negative 1/2, divided by negative 1. So I'm going to end up with 0 over negative 1, which is just 0. Okay, so by using this method, what we've done is we've taken a difference up here, turned it into a product, which we then wrote as a quotient. And once we had it, the function written as a quotient, we could apply L'Hopital's rule. So that's what we did down here. By taking the derivative of the numerator and the denominator, and we end up with a limit that's equal to 0. So now let's do a second method, and the second method is maybe a little more straightforward, and it's probably more in line with what we would have done when we were first working on limits. Okay, so same limit. We still see that this is infinity minus infinity, and we're still going to multiply by the conjugate, x plus square root x squared plus 1. Divided by x plus square root x squared plus 1. Okay, so this is the approach we probably would have taken when we were first working on limits, multiply by the conjugate and see where that leads us. In doing so, so when we multiply the numerators together, I'm going to get x squared. The middle terms are going to cancel, and then the last terms I just get minus whatever the common radicand is, so x squared plus 1. And then in the denominator, we're left with x plus square root of x squared plus 1. In the numerator, this is going to cancel with this. So let's see, by direct substitution here, I'm going to end up with negative 1 in the numerator. And then in the denominator, I'm going to have infinity plus infinity, or just infinity here, which is negative 1 divided by a really big number is going close to 0. So that way, seems a lot more straightforward, perhaps. But it's good to know that we can approach a limit like this in more than one way and end up with the same correct answer.